Welcome to Math 361, Statistical Methods 1. This is the Week 7 online video lecture covering Section 7-3 in the textbook on estimating population means and the t-distribution. Let's review once again the central limit theorem. The mean of a random sample is a random variable whose sampling distribution can be approximated by a normal distribution. And furthermore, the larger the sample, the better the approximation will be. In other words, x bar is normally distributed with mean mu, the underlying unknown population mean. So x bar is a unbiased estimator for mu. And the standard deviation of the sampling distribution is sigma divided by square root of n, where sigma is the standard deviation of the underlying population. There are some caveats to applying the central limit theorem. Excuse me. All the values must be sampled randomly. Sample size should be at least 30. This is more important if the underlying population distribution is skewed. If sampling is done without replacement, as it usually is, we want to make sure our sample size is not too large. And finally, if the population happens to be normally distributed, then any sample size would do. We don't have that n greater than or equal to 30 requirement. Even a sample size of 3 would work. So what we want to do today is talk about creating confidence intervals for population means. The argument is very similar to creating confidence intervals for population proportions. And so in this picture, we're assuming we're either, because the population is normally distributed or because we've invoked the central limit theorem, we are modeling the sampling distribution for x bar as a normal distribution. It is centered at the unknown population mean mu, and it has a standard deviation of sigma over radical n. So the empirical rule applies once again. Within 2 standard deviations of the mean, we should find 95% of all sample means. So I've highlighted one in green, that green box. Let's suppose that's the x bar, the sample mean from our data. And so if I create an interval centered at this sample mean that stretches out 2 standard deviations. Now the standard deviation here is not sigma, it's sigma over radical n. So it's stretching out 2 standard deviations of the sampling distribution. It should contain the true unknown population mean mu. This is my 95% confidence interval for mu. It's constructed the same way as before with population proportions. My confidence interval is an estimate plus or minus a margin of error. In this case, the estimate is not p hat, it's x bar, plus or minus. There's a critical value, z alpha divided by 2, and then times this standard deviation of the sampling distribution, sigma over radical n. Just like when dealing with population proportions, we have an issue in that the standard deviation of the sampling distribution requires quantities we don't know. Here we have sigma, which is usually an unknown parameter. So what we'd want to do, just like we did for confidence intervals for proportions, is we'd want to replace sigma with our sample standard deviation, S. And the question is, can we do that? When we were working with a population proportion, the issue really came down to just our endpoints changing a little bit for our interval. And so what happened is we didn't really get a 95% confidence interval for P. It was really like a 94.7% confidence interval or a 96% confidence interval. The idea that we replaced the radical PQ over N with a radical P hat Q hat over N just changed those endpoints a little bit, but in the end, we were still able to go ahead with our analysis. However, while this is how it was originally done, just replace sigma by S, it turns out we cannot do that here. There's an issue. And the issue stems from this fact. If we took x bar as a random variable and tried to standardize it, right? X bar minus mu divided by sigma over radical n. right? That is a standardization of the sampling distribution for the statistic X bar, right? That standardized random variable will be normally distributed with mean 0, standard deviation 1, if X bar starts out being normally distributed. And that holds either if the population distribution is normally distributed or if we've invoked the central limit there. However, what happens is when we replace sigma by S in that denominator, even under those two conditions, X bar minus mu, now divided by S divided by radical n, happens to not be normally distributed. So we don't get a standard normal random variable out of this. So using critical values from the standard normal distribution, those z-scores, is incorrect. The problem here is that replacing sigma by S introduces some extra variability. S is another statistic that is calculated on our sample, and therefore S has its own sampling distribution, which turns out to be not normally distributed, something called a chi-squared distribution. We didn't cover that in class, but there's extra variability here because S comes from a sampling process just like X bar. That wasn't an issue with estimating population proportions, because even though we had to estimate the standard deviation of the sampling distribution, radical PQ over N, to estimate that, we used p hat again. Here, to estimate sigma by S, we don't use X bar. So, whereas in proportions, p hat gives me some knowledge about estimating the standard deviation of the sampling distribution, here, X bar tells me nothing about estimating the standard deviation of the sampling distribution. So what we need to do is have a model that's similar to a standard normal distribution, but adds in some extra variability. It turns out that the model we need is something known as a t-distribution, sometimes referred to as a student's t-distribution, because the original creator of it, a man named Gossett, who worked for the Guinness Brewery Company, was not allowed to publish his results under his own name, so he used the pseudonym Student. So student's t, or just the t distribution here, as we see from this picture, this is a plot, a graph of its probability distribution. It's unimodal and symmetric about t equals 0. It looks like a standard normal distribution, but it has fatter tails out at the extremes. And it turns out a t-distribution is actually an infinite family of distributions, each one determined by what's known as the degrees of freedom. So in this drawing here, we see that the dotted line has df, or degrees of freedom, equal to 3. The dashed line has df equal to 10, and then the solid line has an infinite degrees of freedom, which happens to be equal to the standard normal distribution. So the idea here is a t-distribution has, or models, more variability, fatter tails, but as the degrees of freedom increase, it starts to approach a standard normal distribution. This is the tool we will need to create proper confidence intervals for unknown population means. Now there's a catch, and the catch is this. To use a t-distribution, we must assume the data comes from a nearly normally distributed population. So when we have small sample sizes, we have to be very careful about what our sample distribution looks like. If we see our sample distribution is totally skewed, and our sample size is in like the 20s, we should not be using this approach. Now, how do we check this condition? Well, obviously we don't have the entire population distribution, or else we wouldn't be doing this. We can check by creating a histogram, or something called a normal probability plot. This was in section 6.6 in the textbook. We didn't really talk about it in class, although I'll show you an example in a few minutes. So we'll create a histogram or a normal probability plot for the sample data. And if it looks like it's fairly close to being normally distributed, we'll assume we're in the okay to use a t-distribution. Now, if we believe that the underlying population is not very normally distributed, what we'll want to do is just to have a larger sample size. It turns out that this requirement of a normally distributed population is an okay one to violate. It's not a very strict criteria here. So if we work with this and everything checks out, all our assumptions are met, what we create here is something known as a one sample t-interval. Contrast that with when we were estimating population proportions, that was a one proportion z-interval because we used a standard normal distribution to come up with those critical values. A one sample t-interval instead uses the t-distribution. Now all we'll need to know is what are the appropriate degrees of freedom. Well, as we'll see here, the degrees of freedom happens to be equal to the sample size minus 1. So if we sampled 50 individuals, our degrees of freedom would be 49. So on the left here, we see that our confidence interval, once again, is an estimate plus or minus a critical value. This time it's t alpha divided by 2 instead of z alpha divided by 2. Now times a standard error. And remember, the standard error terminology really just means we're taking a standard deviation of a sampling distribution, in this case sigma over radical n, and replacing sigma with an estimate s. So now what I'd like to do is turn to R and look at an example of creating a confidence interval for an unknown population mean. To demonstrate how to build a one sample t-interval, we will use a data set that comes pre-installed with R. To see what data sets are available in R, type the data command and empty parentheses, and a window pops up. It says data sets and package data sets. The left column lists the names of the data sets. The right column has a brief description of them. Scroll all the way down here, we're going to use the trees data set. This is the girth, height, and volume for black cherry trees. And we'll focus on height, which is given in feet. So to get the trees data set into our workspace, we'll use data and now trees, the name of the data set. Hit enter. I didn't save that as a variable though because it automatically brings a trees variable into my environment. If I want to look at the first few rows of the trees data frame and type head trees, see I have 3 columns, one for girth, that's technically, actually that's mislabeled, that should be diameter, height and feet, and volume. So we're going to focus on height. So let's save the tree heights to a new variable, $height. Now, if I just wanted an estimate of the mean black cherry tree height for the population of all black cherry trees, I could find my sample mean by typing mean of height. So I see that my sample mean is 76 feet. Now, to construct a one sample t-interval, I first need to check to see if all my assumptions are met. So that means I'd like to see if I have any evidence that the underlying population of tree heights is normally distributed. And if not, then I want to check whether or not I at least have enough data points so that I can invoke the central limit theorem. So to do this, I could create a histogram of the tree heights. And I see that it is unimodal. It's not entirely symmetric. It looks like it's skewed a little bit to the left here. There's not many data values either. I see that there might be about 30 or so total. I could also make a box plot, and we'll make it horizontal. So I see that the stem on the left here, or the whisker on the left, is a little bit longer than that on the right, so it is skewed a little bit to the left. But if I look at the middle 50% of values, it does seem pretty symmetric within that middle part there. A final way of visualizing whether or not my data comes from an approximately normal distribution is to create what's known as a normal probability plot, although these are sometimes called quantile plots. So the command in R is QQ_norm, and then my data set. And I always want to do QQ_line in the data set as well. So the idea here is that if my data were to come from a normal distribution, most of the values should follow this line fairly well. I should see no systematic deviations from that straight line. Notice here I see a little dip on the low end here. That's that skewed to the left nature of the distribution we saw. Now I should note what we're actually looking at here in this normal QQ plot. I see theoretical quantiles along the horizontal and sample quantiles along the vertical axis. So really what it's comparing is a hypothetical normal distribution whose mean is equal to the sample mean and whose standard deviation is equal to the sample standard deviation, right? It's comparing that to my data set. So if I had a particular value, say 72 feet, I could see what percentile, where does that 72 fall within my data set? Right, that would be this vertical axis there, sample quantiles or percentiles. I could then also say that, look at, okay, if I had this normal distribution that's centered at 76 feet and has the same standard deviation as the sample, where would 72 fall within that normal distribution? Right, what would its percentile be there? And I can compare the percentile of that value between the sample data and this theoretical normal model. And if they are about the same, then I should see a point that is somewhere near this line. Right? If all these points lay precisely on this straight line, then I would have an exact normal distribution I was working with. So I look at this and I say, okay, it falls on the line fairly closely, a little tail off over here in my lower ends, a little skewed to the left. But overall, it seems okay. I think I can go ahead, create a one sample t-interval, and trust my results. So now to create the one sample t-interval, I need to know that calculation. Once again, it's an estimate plus or minus a margin of error. So what quantities do I need? I need x bar. That'll be the mean height. I need n. That'll be the length of height. How many values do I have? I need s, and that'll be the standard deviation, the sample standard deviation of the height data set. So if I want to create a 95% confidence interval, the left endpoint of that would have to use a z inverse of 0.025, and the right endpoint would need a z inverse of 0.975. That's how I would get the critical values I want in there. So what I'll do here is the following. To create the left endpoint of my interval, I will start with my x bar, and now I will subtract off. Now I need the inverse z command, but not on the calculator in R. So that is the quantile function. So QNorm 0.975. But I need to remember is that I'm not using a normal distribution though. I should be using a t distribution. So actually that should be QT 0.975. Now I also need to give it the degrees of freedom. That's equal to n minus 1. So that's my critical value times now the standard error, which is s divided by square root of n. Now the right endpoint, that would be x bar plus qt 0.975, degree of freedom equal n.1 times s divided by square root of n. All right, that's just the formula from the slide. So see my left endpoint is 73.662. My right endpoint is 78.3372. So I'm 95% confident that the mean height of black cherry trees is between 73.5 and a little over 78 feet. Do I know precisely if it's in that interval? I do not, but that is the best I can say. All right, so it's always come up with your estimate, verify that your assumptions are met, and then go and create your confidence interval, making sure you have the correct critical values. I was saying this with the QT function here was like the Z inverse. I should say it's like the T inverse function on your calculator, which I'll show you in the next example. So in R, the easiest way to create these intervals is to literally type in the formula and get your confidence interval that way. So now that we've seen how to create a one sample T interval in R, let's go to another example and then we'll see how to do it on our graphing calculators. Hoping to lure more shoppers downtown, a city builds a new public parking garage in the central business district. The city plans to pay for the structure through parking fees. During a 2-month period, 44 weekdays, daily fees collected average $126 with a standard deviation of $15. The first question is, what assumptions must you make in order to use these statistics for inference? So we are looking at this 2-month period, 44 weekdays, as a random sample from some population distribution that consists of daily revenue from parking fees. We're told that X bar is 126 and S is $15. Now, what I need to assume are the following. First, I need to assume that the daily fees collected in each individual day is independent of the daily fees collected on other days. Now, this is probably violated because you can imagine there might be a conference in town where there are, for a few days, where there's a lot more people using the parking garage, and so revenues might be up on those days. And then maybe another week later, there was some construction outside of the parking garage, and therefore fewer cars were able to access the parking garage, decreasing the fees in those days. So the independence assumption, we probably should mention in our analysis, has a very good shot of being violated. The other consideration is that since we don't know the population standard deviation, when constructing a confidence interval, we'll need to replace that with S, meaning we'd like to use a T distribution. But that requires a nearly normal population distribution, which I have no knowledge of here. So we'll have to assume that, or a very large sample size, but 44 isn't that large. So there are two kind of critical assumptions we're making here: the independence of one day's revenues versus another's, plus the underlying shape of the population distribution. We're going to have to just assume that is at least close to being normally distributed. Writing 90% confidence interval for the mean daily income this parking garage will generate. Interpret this interval within the context of the problem. So to calculate this, we'll move over to the graphing calculator. On the graphing calculator, we need to go to Stat and arrow over to Tests. Recall previously we used a one proportion Z interval down here, option A, for finding a confidence interval for a population proportion. Now we're going to arrow up and use a T interval. Now I have two ways of doing this. First, I can have my input be some data. So list L1, confidence level, and so forth there if I had the data entered into the calculator. But I don't have any raw sample data. All I have are the summary statistics. So instead, I'll arrow over to Stats, and that allows me to enter the information here. So X bar, I was told, was $126. The standard deviation, sample standard deviation, was $15. And the sample size was 44. And I believe now the problem asks for a 90% confidence interval, so let's put 0.90. Now we arrow down and calculate, and we see that my 90% confidence interval is $122.20 to $129.80. So the way I interpret this is that I am 90% confident that the true mean daily revenue for this parking garage is between $122 and almost $130. Now, do I know precisely whether it's in the interval or not? No, I never do, but this is the best I can say. Remember, those confidence intervals are always statements about an unknown population parameter. So in this case, it's about mu, the mean daily revenue obtained through parking fees. Now, the next question says, the consultant who advised the city on this project predicted that parking revenues would average $130 per day. Based on your confidence interval, do you think the consultant was correct? Well, let's go back to our answer here. I see that my interval almost contains 130 there, but it's near the tail end. So my best statement I could say here is that while it's possible that we could average $130 per day, that seems to be a high-end estimate, and the evidence we have does not fully support that. However, I would caution that this was based on 44 weekdays, relatively small sample size, and there are several assumptions that we have had to make which may not be true. Now, the same problem says someone suggests that the city use its data to create a 95% confidence interval instead. How would this interval be better for the city? So we need to remember here that the margin of error is this critical value, T alpha divided by 2 times S over radical N. So by increasing our confidence interval, we are actually increasing the value of that critical value. Now, since S and N are fixed in this assumption, in this problem here, increasing the value of the critical value will increase the margin of error. Meaning, to be more confident in my interval estimation, I have to be less precise. There's always this trade-off between precision and confidence. And so here, I would result in a larger margin of error, but I'm more confident. So I would have a larger margin of error. The city would, however, have much more confidence that the true mean is somewhere in this interval. Now, how would this be worse for the planners? Well, like I said, to be more confident means you have to be less precise. So if we're looking at our revenue forecasts, our revenue forecasts will be much wider because of this less precise interval. So for questioning whether or not we actually will be able to pay for the parking structure, we might run into some problems there because of the lack of precision. Now, how could they achieve an interval estimate that would better serve their planning needs? Well, I don't want to have a wide or a very large margin of error. So if I go back and look at this quantity again, if I increase the critical value to become more confident, that's an increase the margin of error. The only other two quantities I can manipulate are S and radical N. So S is kind of fixed due to my sample. So I could look at possibly getting more data. That's my last possibility, that radical N in the denominator. By increasing the value of N, I decrease the margin of error. So by becoming more confident, increasing my margin of error, I can compensate by getting more data. However, that's divided by square root of N. So I would need to increase my sample size by a factor of 100 just to decrease my margin of error by a factor of 10. All right, so that square root, some diminishing returns because of that square root there. Now, how many days worth of data could they collect, or should they collect, to have 95% confidence of estimating the true mean within $3? Well, if we go back to our data over here, it looked like we were about within $4 in our original estimate at 90% confidence. So to get our estimate within $3, I'd have to look at that margin of error, which actually is incorrect on this slide. I forgot the z-score on there, or sorry, the t critical value is not on there. But I want that t critical value times S over radical N to be less than or equal to $3. Now, unlike with estimating sample sizes for proportions, where I could just, if I had no previous guess for p hat, I could plug in p hat and q hat as 0.5 in that formula. Here, I really have no idea what to plug in for s unless I already have some data. So in this case, because we already have this sample of 44 weekdays, to calculate this, I would put the t alpha divided by 2's critical value in there, and s I would use as $15 since we already have that, and I would leave n as the variable I want to solve for. Okay, when we start class on Saturday, we will work on some group work to look at another example of both interpreting confidence intervals again, making sure we know what we can and cannot say when we create a confidence interval, and then another example of creating confidence intervals for population means using the t-distribution.